Let's begin by exploring how text is transformed into vectors, a core concept for understanding embedding models. So, at its heart, an embedding model is basically a neural network, often using that transformer architecture we've talked about. Its main job? It takes text, breaks it into these things called tokens, and then maps them into a high-dimensional space. Think of it like giving each piece of text, say a sentence, its own coordinate in a space that could have hundreds or even thousands of dimensions. Now, here's the really cool part about this vector space. The distance between any 2 points tells you how similar their meanings are. So, if two pieces of text are alike, their vectors will be close. This also means the model can get those subtle differences, like how bank can mean a place for money or the side of a river, just from the surrounding words. Essentially, embedding models give us a mathematical way to represent meaning in text. It's way more powerful than just matching keywords. It's about understanding the actual concepts. Now that we understand how text becomes vectors, let's see why this is so crucial for retrieval augmented generation, or RAG. Okay, so traditionally, search has relied on matching keywords, right? Think algorithms like BM25. But vector similarity search, using those embeddings we just discussed, offers a much smarter way. It's key for really getting what a user means, even if they don't use the exact same words as the documents you have. There are a few big advantages here. First, it handles all sorts of language variations really well. Synonyms, paraphrasing, different terms, they all end up close in the vector space. Second, it opens the door to using other types of data, like images, in the future, by representing them in that same space. And finally, it turns a really complex text matching problem into a much simpler, efficient math problem. We've seen what embeddings are and why they're useful in RAG. Now, let's trace the data flow and understand where the embedding model fits in. So, during the ingestion phase, which happens behind the scenes, we take the text chunks. We feed them into our embedding model, and out come the vectors. These vectors then get stored in a special type of database, a vector database, all ready for when we need them. Then, during the inference phase, that's when a user actually asks a question. We use the exact same embedding model. We turn the user's query into a query vector. This vector is then compared against all the document vectors in our vector database to find the most relevant stuff. And this consistency is super important. Using the same model for both ingesting documents and processing queries makes sure the whole system stays aligned. That way, things with similar meanings really are close together in the vector space. This little code snippet shows you the basic idea. You import sentence transformer, pick a model, like this all-MPNet-based v2, which is pretty good for general understanding. Then, you give your text chunks to the model's encode method, and what you get back is a list of numbers. These are your embeddings. Just a heads up, the number of dimensions here, say 768, needs to exactly match what your vector database is set up for. This diagram here gives you the big picture of the RAG flow. You extract and chunk text, send it to the embedding model for offline processing into a vector database. Then, when a user query comes in, it goes through that same embedding model. The resulting query vector is used to search the vector database, and you get your relevant results back. Integrating embedding models into a RAG system involves several engineering trade-offs we need to consider. Let's dive into those. One big limitation is the maximum input length, or sequence length, most models have. Many can only handle, say, 512 tokens. If your text chunks are longer than that, the model will just cut off the extra text and you'll lose information. So, your chunking strategy really needs to keep these limits in mind. Then there's the balance between how many dimensions you use and how fast things run. More dimensions can capture more detail, sure, but they also use more memory and computing power, which can slow down retrieval. For systems that need to be quick, smaller, denser vectors, maybe around 768 to 1024 dimensions, are often a good sweet spot between accuracy and cost. Finally, you have to decide between using a general-purpose model or one that's specific to your field. A general model might not quite get the jargon in, say, finance or a technical industry. In those cases, a model that's been tuned or fine-tuned for that domain can really improve understanding and performance, although it might take a bit more work to set up. Finally, how do we know if our embeddings are actually any good? Let's look at how we evaluate them, focusing on the primary metric. The main way we check how well embeddings are working is with cosine similarity. It's a measure of the angle between two vectors. A score of 1.0 means they're pointing in the exact same direction, totally similar meaning. A score of 0.0 means they're unrelated. The formula uses the dot product and the magnitudes of the vectors. You'll want to watch out for low similarity scores, maybe anything below 0.6. These could be a sign that your document chunking isn't quite right, or that the embedding model just isn't a good fit for the kind of data you're working with. So, to wrap up, embeddings are key for turning text into something searchable. Keeping your embedding model consistent is vital, and the model you choose affects both accuracy and how fast your system runs. Those are the main things to remember.